This question's from Unit 3 2024 paper of the A2 Physics course, and it's from the God, I hate this bit. You've got to say something at the beginning so everyone can tune out of your video and then move on to something else if they need to. This question from the 2024 Unit 3 paper is all about the energy contained within nuclei, so the nuclear binding energy or the energy released during nuclear reactions. And it's quite a straightforward one. It's question 1, so there's not too much in here to trick us, but there is lots of button pushing on your calculator to go with this one. So first thing it wants us to do is it wants to consider this equation here. So we've got some reactants on this side and we've got some products over on this side. And what it wants me to do is it wants me to calculate the energy released. So how much energy is given out as this side becomes this side, as my reactants become my products. It wants me to give my answer in MeV. That's going to be quite important. And helpfully, they've given me the conversion to MeV in the question here. They've also given me loads of information here. So the first thing I'm going to do is I'm going to calculate what is the energy of the left-hand side. And then over here, we'll do the right-hand side in a second. So the first thing I need to do is the neutron, the first thing I've got here. So that's going to be from the question 1.0. Okay, and I'm going to add to that the mass of my uranium nucleus, which is going to be, again in the question here, 2, 3, 5. Okay, and when I add those together, I find that the whole of my left-hand side is equal to 236.052592. Keep all of your decimal places at this point. That's, of course, in U. So now if we do the right-hand side, we're going to have that one, which is 40. We're going to have the krypton. Obviously, we're adding those together. Be careful, because we've got 3 neutrons, but then we've got the neutron again. Okay, all of that goes into your calculator, and you end up with 235.866563. Now, you can, of course, chuck it all into your calculator and go from there. The exam board doesn't mind you doing that, but just be careful, because if you make a mistake, no one can see what you've done. So now I'm going to do my left hand minus my right hand. So I'm going to do 236 minus this one over here, and that's going to give me 0.186032 U. 1 U is 931, so times that by 931, and that will give me my answer in MeV. That's 173.2 MeV. Okay, relatively straightforward. Lots of button pressing on your calculator, but not too bad once you get into it, once you know the process that you're using. Next bit is a little bit trickier. You need to do a little bit of something that looks a little bit like some chemistry here. We need to consider how many nuclei there are. So the number of nuclei in 1.2 kilograms of uranium-235 is going to be equal to the Avogadro's number divided by the 235 bit. So that's the mass of 1 uranium. Except careful, because that's in grams. So this is going to be 235 times 10 to the minus 3 grams into kilograms. And just for good measure, while we're here, we'll times it by the 1.2 kilos that they're telling us we've actually got of the uranium. Again, into your calculator that goes, and that's going to come out with 3.074 times 10 to the 24 nuclei. So that's how many nuclei of uranium there are. We've just worked out that each one of these releases 173.2 MeVs. I won't put that in. When I equal that, or when I press equals on my calculator, that's going to give me 5.32 times 10 to the 26 MeV. It wanted it in joules. So what I now need to do is convert between the two of those. So if I do my 5.32 times 10 to the 26 times 1.6 times 10 to the minus, I'm going to use times 10 to the minus 13 because that will take care of the m from the MEV. And that will all come out as 8.52 times 10 to the 13 joules. Okay, if you've done times 10 to the minus 19 over here, because you're using the the charge of an electron, this would come out looking a little bit different here. Your standard formula is different, and it will be giving you megajoules. Because they want us to do joules, I'd stick with that there. So they've not quite finished with us yet. We've got part C to this question. What we're going to do here is consider whether or not we can power 2 billion 11-watt light bulbs for an hour. So there's different ways you can do it. If you look through the mark schemes and stuff, they'll show that there's different routes through this. But the way I'm most comfortable at doing this is considering how much energy is used by these light bulbs. So 11 watts is 11 joules per second. So for an hour, that's going to be 11 times 3,600. And that will give me 39,600 joules used in an hour. Okay, I'm just making little notes to help me understand what I'm doing as I go along here. Okay, so then I considered, well, if that's 1, how many will 2 billion use? So if I take that answer and times it by 2 times 10 to the 9, which is 2 billion, that's going to be 7.92 times 10 to the 13 joules used by 11 billion. Okay, sorry, not 11 billion, used by 2 billion. The 11's come from the watts, hasn't it? And then if we think about it for a second, that's the total energy used in an hour by these things. And I'd just like to make a statement at the end. So 7.92 times 10 to the 13 joules is less than, if we go back to part B, it's less than this 8.52 times 10 to the 13. It's less than 8.52 times 10 to the 13 joules. Therefore, it would be true. They could do this, couldn't they? Okay, so that takes us through to the end. A nice little finish here, which relies on you being able to sort of visualize what's going on within the problem. Think about, it's a little bit synoptic. It's got a bit of Unit 2 in it. It's just a bit of a, can I use my physics understanding to demonstrate the answer to a problem? Okay, hope you've enjoyed that one. Go and have another exam question now. Go and do some more practicing. Bye now.